This is lecture 37 of Condensed Matter Physics 1. And we continue with our discussion of dynamics of electron in a band. In lecture 36, we discussed how the velocity of an electron in a band changes when a constant field is applied. We also derived general equations of motion for describing the motion of an electron in a band. And using that, what we are going to do in this lecture is introduce the concept of effective mass, and through that, how when a band is almost completely filled with some vacant states on top, how the motion, the collective motion of all these electrons can equally well be described by the empty states, and these are then given the names of motion of holes, and the two are absolutely equivalent. It's just that in an almost filled band, the number of holes or number of vacant states are much smaller. So, it becomes much more convenient to describe the motion in terms of these empty states, and it also has consequences. We will be discussing all that in this lecture. So, to start with, what we have learned that in a band, the velocity of an electron at k is given as 1 over h cross grad of E k, which in 1D becomes equal to 1 over h cross d E by d k. And h cross d k by d t is equal to the force, and in an electromagnetic field it will become minus E plus V group cross B. If these are the two equations, then let us ask what is the acceleration of an electron. And when I say electron, I mean electron in this band. Let me again confine myself to 1D. So, acceleration A would be d V group by dt, which will be d V group by dk dk dt. Now, if I write it further, so then acceleration, which is d V group by dk dk dt, I can write this as 1 over h cross d 2 E by dk square, and dk dt is 1 over h cross f. I have used V g equals 1 over h cross d E dk. I can write this as equal to 1 over h cross square d 2 E by dk square f. Compare this with A equals f over m, and this tells you that 1 over m is nothing but 1 over h cross square d 2 E by dk square. Let us check for free electrons, where E is h cross square k square over 2 m, and this checks. But in a band, it is very interesting that 1 over m need not be equal to 1 over m free. So, when I write 1 over m equals 1 over h cross square d 2 e by d k square for free electrons, it checks. And if I am talking about a band, then it will be different at different points, depends on the curvature of the electric field of the energy versus k. So, this is called introduce the concept of effective mass and call this 1 over m star is equal to 1 over h cross square d 2 e by d k square, where m star is the effective mass of the electron, of course, in the band. So, the electron responds with this kind of mass. Why is the mass different? Physical reason is that electron is not only responding to the applied field, it also is exchanging momentum with the crystal lattice. And I told you to read about it from Kittel's book last time. Again, reference is Kittel chapter 8, where he explicitly talks about why h cross k dot equals f works. It works because k dot represents the total change in momentum. So, this electron is also exchanging momentum with the lattice, and therefore, it could be more sluggish, it could be heavier, or if it is pushed by the lattice, the momentum is given to it by the lattice, it will become lighter. So, effective mass is different. It actually incorporates in it the effect of lattice interaction, and that is not surprising, because energy band is actually arising because of the interaction of electron with the lattice potential. Now, let us just see what this effective mass looks like. So, recall from lecture 32 to plane wave model of a band. And there, near k equals pi by a, we found the energy by epsilon k minus E, epsilon k minus pi by 2 pi by a minus E minus V 2 pi by a mod square equals 0 gave the band energy, where epsilon k is h cross square k square over 2 m, the free energy. When we worked it out, we found that the energy, the lower band E k for the lower band was E k equals epsilon k plus epsilon k minus 2 pi by a divided by 2 minus 1/2 square root of epsilon k minus epsilon k minus 2 pi by a square plus v 2 pi by a mod square. This is what we found the energy to be. Let us just work it out for certain values. So, let us take for simplicity h cross square equals 1, m equals 1, a equals pi, and mod v 2 pi by a equals 0.1. If you do that, you will find that E k for the lower band comes out to be k minus 1 whole square plus 1 divided by 2 minus square root of k minus 1 whole square plus v 2 pi by a mod square. You put in all these numbers and this is what you get. And the group velocity V g, you can easily work it out, comes out to be k minus 1 minus 1 over square root of k minus 1 whole square plus v 2 pi by a mod square. And the effective mass 1 over m star, h cross we have taken to be 1, so it does not matter, 1 over m star comes out to be 1 minus 1 over square root of k minus 1 whole square plus v 2 pi by a whole square plus k minus 1 whole square divided by k minus 1 whole square plus mod V g whole square raised to 3 by 2. And you plot this. If I plot these quantities, schematically what you are going to get is this. Since I had said in that lecture that these two waves are being mixed for k greater than 0, so I will just plot this from k equals 0 to pi by a. The energy graph looks like this. This goes up to roughly 0.4. The velocity graph, we have been plotting it in the previous lecture also, but nonetheless let me plot it once more. It goes up linearly and then comes down to 0, maximum goes to about 0.7, and m star starts with 1. So, roughly free electron goes up and then comes down like this. This is plus 1 roughly and this is roughly minus 0.1. This is k. What I want you to notice here is that for k near the below zone, m star is negative. And therefore, if an electric field is applied to an electron near k equals 0, it will accelerate in negative x direction for E equals E in positive x direction, but an electron near the top of the band k near Coulomb zone boundary, it will accelerate in positive x direction for E in positive x direction. So, the electron near the top is behaving as if it is a positively charged particle, and that is understandable because near the top of the band or near k equals the Brillouin zone boundary, a lot of momentum from the crystal lattice is transferred to the electrons, and therefore, it may accelerate the other way rather than the normal way. Now, to understand this, let us look at it classically also. Classically, the equation of motion for a particle, charged particle in an electromagnetic field is equal to q E plus V cross B. So, equivalently I can write minus m r double dot is equal to minus q E plus V cross B. So, motion of a charge q with mass m is equivalent to the motion of a charge minus q with mass minus m. Therefore, if I have a situation in a band where the effective mass is negative, it is better to describe this as a particle of positive mass and positive charge and opposite charge, and that is precisely what is done in introducing the concept of holes. And this is what we discuss next. So, to understand this, let us go step by step, and I am following steps given in Kittel's book, with a few things thrown in from my side. If you look at a band, and this has these electrons and a vacant state. The summation over k, all k, is equal to 0 by symmetry. And therefore, summation over k, all except one state, is going to be equal to minus k of vacant state. So, I can assign the k value to this collection of n minus 1 electrons, 1 electron missing, as minus the k of missing electron, or minus k of the vacant state. So, that is point number 1. Point number 2, so let me just write this first. So, for an almost filled band, k for all electrons is equal to minus summation k vacant states. So, I made this point through one vacant state, but then it goes through for the others also. So, that is point number 1. So, whether I talk about, and keep in mind it is very important, I am talking about a band where the sum of all k becomes 0. It is not true in free electron states, but electrons in a band. So, the k for all the electrons can be written as minus the k of the vacant state. If the number of vacant states is less, is easier to count, may as well work in terms of vacant states. That is the philosophy. Point number 2. Energy of a band with one vacant state is equal to the energy of removal of an electron from that state. Right after I have created a vacant state, so I have removed an electron, and therefore, this will be equal to minus the eigenvalue E k vacant state. I can also write this as minus E minus k vacant state. Why? This is by symmetry of the band. I am using the symmetry and I am assuming by now you have seen enough pictures and you know that it is symmetric with respect to k and minus k. So, with these two things, what we are going to say is that treat the missing electron, or even better vacant state, in an almost filled band as representing particles there and call them holes. And these holes, by holes we mean these are like real particles which are going to move. This is convenient to do to represent the motion of all the electrons, because as I said number of vacant states is less. However, the two are absolutely equivalent. By these holes what I am representing is the motion of all these other electrons collectively. It is easier to see, it is easier to work with, and it explains things correctly, and we will establish that equivalence. But for the time being what we are doing then is that if I have a band k equals 0, I have this band where I have these electrons filled and a vacant state. I am writing this as the holes and thinking of them as real particles, and this vacant state is represented by, this was minus k, this is plus k, and this was minus E, this is plus E. So, I am thinking of this missing state as a particle which I will call hole with k value as minus of that missing electron and energy positive E. And so far what you have seen is the description is absolutely equivalent to describing those n minus 1 electrons, because they are in the band and therefore, this satisfies certain symmetries. What about if you want to establish the equivalence? What about the velocity and the equation of motion? So, let us do that. Point number 3, V of the whole, now that I have introduced that word, is going to be equal to V of the missing electron, or V of the vacant state. How so? V of whole is equal to d E whole divided by d k whole, which is minus d E, that electron from the missing state, over minus d k of electron from the missing state, which is d E electron divided by d k electron, which is V electron. And this makes perfect sense, because again if I look at that picture of the bands, this is the electron band, this is the hole band, this is the missing electron, and the correspondingly here is the hole. As the k is increased here, energy goes up, velocity is positive. The increasing k here means decreasing k for the hole, electron goes down. So, the slope is the same, and therefore, the two are the same. Now, point number 4, and that is very important. A, mass of the hole is equal to minus mass of the electron, that missing electron, and therefore, concept of hole is useful as for upper levels, k near pi by a, it gives a particle with positive mass. So, instead of dealing with a negative mass, let us talk about positive mass. How does that come about? Mass of the hole is going to be equal to 1 over h cross square d 2 epsilon whole by d k whole square. This is also related to how it responds to electromagnetic field, but that these are coupled. So, I am just doing mass whole to start with, and this is going to be equal to minus 1 over h cross square d 2 epsilon electron divided by d k electron square. Notice that k whole is minus k electron, but because of its occurring twice, so the sign does not change, and this is equal to minus m e. At the same time, you can also write, and as I said, these are related, part B, and again part A and part B are related, is that whole, and therefore, collectively all the electrons in the band, which is almost filled, respond to an EM field as a positively charged particle. Let us see that. So, let us write d k whole, and remember this whole is again representing all that other electrons collectively. So, the two are equivalent. D k whole d t is equal to minus d k electron d t, and d k electron d t is nothing but 1 over h cross minus E plus V electron cross B. V electron is same as V whole. So, I can write this as E 1 over H cross E plus V whole cross B. So, this immediately tells you that the whole, or again let me keep reminding you, this is representing all the electrons in the band, and again very important, it happens only in the band. Responds like a particle with plus E, that is opposite to electronic charge. This will also give you again the effective mass to be positive, and let us see that. So, if I were to calculate dV whole divided by dt, this will be equal to dV whole divided by dk whole divided by dt, and this is going to be equal to minus dV whole is the same as dV electron. So, dV electron, the missing electron, divided by dk electron, sign changed because k whole is minus k electron, times, we have already calculated the dk whole by dt. So, this is equal to E plus V whole cross B, and dV electron by dt is nothing but the effective mass for the electrons. So, this becomes minus 1 over m star electron times E plus V whole cross B. This I am going to call 1 over m star whole, and this is positive for the near the top of the band, and this is positive charge for the whole. So, whole thing is complete. So, effective mass of the whole is minus the effective mass of the electron, and consequently, I also change the charge of the electron. Now, number 5, we are discussing about current in an almost filled band. So, again by symmetry, what we have is summation V electrons in all states is 0. So, summation of V electrons in almost filled band is equal to minus summation V empty states, and the current density therefore, J, which is equal to minus E summation V electrons in this almost filled band is equal to plus E summation V empty states. So, this implies that current is also given correctly by the holes. So, we made a one-to-one complete correspondence between the empty states representing some particles in an almost filled band and the motion of the rest of the electrons. So, let me just make it once more pictorially. So, suppose I have a band, let us make it like this, in which the electrons are filled all the way up to here. So, motion of electron in this band is equivalent to, and I will shift the whole thing now down. I will make this state like this. This is these empty states. So, let me show them by green. They are like the whole states. These are holes. Motion of holes in their band, and that band is obtained from that empty band like I have discussed so far. So, this is equivalent. So, I can think of this almost filled band will respond as if it has positive charges with positive mass particles. So, it is like, and the mass of the particles is not the same as free electrons, it is obtained by curvature of the energy. So, this response is absolutely equivalent. So, this means that more current and electromagnetic properties can equally well be given by the motion of holes. This is absolutely equivalent. I mean, one is not just saying it for representation, the properties come out to be the same, and it is much more useful therefore, to talk in terms of holes when the number is less, is almost a filled band. Now, one consequence of this, let me write right away, is that in a Hall effect experiment, the Hall coefficient of such a system will come out to be positive, because now these are behaving like positively charged particles, and I want you to recall of BE, Mg, etc., and connect them with their band pictures. This I have discussed while discussing semi-metals, and we will discuss this more, but this is one consequence. Remember that in BE and Mg, some of the electrons from the first Brindle zone were actually going over to the second band and were leaving these holes behind. Those holes actually now give you a positive Hall coefficients. Now, that is one thing, and other thing I want you to do is show that holes can be described by Hamiltonian minus H star. H is the electron Hamiltonian and clock wave function psi k star. And this is to be done by writing the time dependent Schrodinger equation for an electron in an EM field. You do that, you go over the arguments that I have given, then it will convince you that in an almost filled band, it is much better to talk about the transport etc. in terms of holes rather than electrons, and they represent exactly the motion of all the electrons that are in that band. This is good because for holes the mass comes out to be positive. So, it is intuitively appealing, charge comes out to be positive, and they describe the properties absolutely equivalently. So, let me with that conclude this lecture by stating that concept of holes and their equivalence to description of an almost filled band has been discussed. Thank you.